and some of the applications. We're going to talk them through. One of the things that the previous speaker was talking about was big data. That was one word that you used. And then the other word that you used was scalability. You used that a couple of times. And those are very important to us. The volume of data that we take on is quite large. We've been around for 12 years. We have over 300 clients. Some of you in the room might actually be clients, either in the financial institutions that we serve, or in retail. We have quite a number of clients in the retail space. And in those spaces, what they're doing is that they're actually providing all of their data to us for us to host. So we are a cloud service. We are a software as a service. And we're providing them the ability to analyze their own data regardless of the volume. And I'll let that sit for a moment and focus in on what we're going to show you tonight. New York Stock Exchange was one of our first clients. They go back at least 10 years with us, 11 years. And we have every single trade, every single quote on the New York Stock Exchange since then. That's 1.5 trillion rows of data. That means that if I want to look at every trade since 2003, the last 10 years, I can put it up and you can take a look at it and you can start to analyze it. The notion of data discovery and analysis is what we focus on. The ability to do that on substantially large data sets is what we focus on. That's what we're going to show you tonight. So what we're doing is we're going to open up, actually Chris is ahead of me, we're opening up a table here, and it has 52.2 billion rows of data. So for those of you who are technologists, and I see a couple of smiles in the room, 52 billion rows of data in one place, in one table, is pretty large. Agreed? Being able to actually arbitrarily navigate, so if Chris goes up and down on the bar here, and actually moves up and down, you can see that he's now looking at row 40 billion, whatever, out of 52 billion. So the speed with which he's moving is the speed with which he's clicking. Think about what that means in terms of your ability to actually analyze data. We have to be scalable, obviously. This is running on 6 machines, by the way. 6 servers, $150,000 worth of hardware. So what we're doing is we're opening up the data. We're letting you actually do every kind of analysis you can possibly think of on this data as if it's a database, which it is, as if it's an analytical space where you can analyze stuff, which it is, as if it's a reporting device, which it is. So all of those capabilities rolled into one. That full stack that you would normally build, starting from floor space, all the way to ability to do analysis, statistical analysis of data in one place on that size of data. So what we're going to do is we're going to actually take on a question on that data. And we're going to go through the steps and we're going to basically build up the analysis with you. So as we're talking it through, you'll see exactly what we're up to. So what we're going to do is first we're going to create a computed column. What that means is, like any other database, like a spreadsheet, what you would want to do is you want to basically compute something. What he's computing is, he is computing the difference between, well, first what he's doing is he's trying to figure out what the last trade was. Relative to every trade, what is the last trade? So this one was at 40 bucks, the last one was at 43.9. If you were going to do that on a data set this big, 52 billion rows, in SQL, what you would normally do is you would do a self-join. Agreed? Disagreed? That self-join is exceedingly expensive on 52 billion rows of data. So what we're going to do is we're actually going to do that computation. Actually, you already did the computation. All right, you're not supposed to get ahead of me. The point is that it's exceedingly fast. And we're going to sort of drill that over and over again in the course of the conversation. So he's actually computed the equivalent of a self-join on 52 billion rows. This is what we call a G function. A G function is a group function. We actually executed something on a group of rows. In this case, one row at a time. The group was tiny. But a group of rows. So this is important to keep in mind. The ability to take these large leaps, intellectual leaps of what it is you want to analyze and how you want to analyze it. This is part of the interactive behavior that the platform has. And we think that's very important for data discovery, for ability to analyze data sort of at will. The next thing he's going to do is that he's going to actually compute another column which is going to compare the price from the last trade to the current trade. Why? Because we're trying to measure volatility. We're trying to see which stocks are actually the most volatile stocks in the S&P 500 for a particular year. For some reason, we're interested in that question. So he's basically doing the absolute value of the difference divided by the previous price. Simple, straightforward. Hit submit, and it's done. 52 billion rows. So the computation of a percentage on 52 billion rows on $150,000 worth of hardware. Pretty fast. So what does that mean? As we're going through this, I really want you to start to think about what this means if you're trying to do some sort of discovery, some sort of analysis on a large body of data. That's how you want to think about this. So what we're going to do next is basically narrow down the population that we're interested in. We're going to narrow it down from 52 billion rows down to a smaller subset. We're going to choose, what year are we choosing? 2005. So we're going to pick 2005 from day 1 to the last day of the year. So 12 months worth of data out of the 10 years that we were looking at before. We're going to narrow it down to 12 months. We're going to do the select. For those of you who are database folks in the room, if I'm doing a select, what am I doing? I have to go through all the rows of data. I have to figure out what my subset is. So go ahead and select. And what I'm doing is it's going to take the 52 billion rows and it's going to return the 1.9 billion rows that are relevant. Now, we're doing this without indexing. Any database guys in the room? All right, how many of you build databases without indices? Not a normal way of doing it. We're also generating, as the process is going forward, we're actually generating code in the background. And we're hanging on to it. Because we figure we're going to come back to it later, we're going to use it for something. We're either going to put it into production, or we're going to finish our analysis and it'll be so brilliant that everybody would want a copy of the results, or we want to change the parameters of it. Any number of those things are possible, so we're not going to throw away this stuff. So go ahead to the next step. You can type before it's cool to type. So what we're going to do is we're going to look for volatility measures that are greater than 10%. That's what we're defining as volatility. Now you can change that definition. Later on we'll change that definition. We'll try it with a bunch of different numbers. But for now, I want to just take that 1.9 billion rows and I want to narrow it down just to the guys that have the highest volatility. And that's the 10%. I care about that. And I also want to know how many times that volatility threshold has been surpassed over the course of that year that I was looking at. So I care about that. That's my real definition of volatility. That's where I want to focus. So 109,000 rows were selected. Now we're going to tabulate that population, and we're going to figure out from that 109,000, I want to figure out exactly how many times each of the tickers actually went past the 10% mark. So that tabulation is done, And we're now looking at the overall population. We can rank, or we can sort them according to how many times they went past the 10% mark. In this case, 3 of them went past by a huge number. Those are actually test stocks that the New York Stock Exchange deliberately puts in to keep track of how the systems are working. So all the automated trading that's going on, they care about deeply. So this guy, for some reason, is very, very volatile. I don't know who they are. Maybe somebody in the audience does. But the other thing we want to do with this is still not the S&P 500. This is the overall universe. So we're going to now link this, we're going to join this result to something else. So what we have is basically the S&P 500. There's 500 rows of data in here. We have the symbol, the company, and the sector in the database. And what we're doing is basically a simple join between those 2 tables. So Chris is going to do that join for you. But while he's doing that, I want to make sure we understand sort of the kinds of things that we just did. We did selection. We navigated through a database that has, one of its tables is 52 billion rows of data. We did a bunch of computations. The computations, we have over 250 different functions that you can deploy. So there are really no boundaries in terms of the expressiveness of the language. So you can, in fact, compute arbitrary things. It could be string related, you can do string manipulation, you can do numerical manipulation of many, many different kinds. You can do regressions, you can do pretty much any kind of analysis. So that's what the help facility is basically taking you through that. There's a tremendous amount of, I showed you one of the G functions that, that we have. That's actually, there's a family of G functions and time series functions that are also possible. And those provide you with the ability to really solve problems in massively parallel ways. And that's where really the bulk of the power of 1010 comes to life. So these are some of the machine learning things that we can do. There's more on the way, and because of the expressive power of the language, basically you have the option directly in the macro code, directly in the query language, to express fairly sophisticated algorithms. So Chris here actually put together a PCA in less than 50 lines of code, for those of you who know what a PCA is. And he also put an autoregressive model modeling algorithm together in less than 10 lines. And we'll show you what that language looks like in a minute. So what we have, so you did the join, you're about to do the join. So that's the join is done. And what we're looking at is basically that full population. Now we know, we did a join with a select. Basically means that it's the equivalent of a left join. So we were only going to keep the guys that ended up having an equivalent on the other side. We used one thing to join, which was the symbol itself. But it could be any number of variables that you use to do the join. There's really no boundaries on that. And we did one join, you could do 100 joins, 1,000 joins, as many as you want. It'll eventually get expensive at some point, but you can do it. So if we can save this so that we can share with our colleagues, what does that mean? I want to parameterize this query, and I want to save it so that I can hand it over to somebody else. Maybe you're not interested in 2005, you're interested in 2006. Maybe you're not interested in volatility being measured 10% being the threshold. Maybe it should be 9%. Maybe it should be 12%, and so on. So what he's doing right now is he's actually going through, he is making modifications to that, and he's going to save that as what we call a quick query. And that quick query is going to have a pretty interface right off the bat, which is going to give you all of that query encoded. But before he does that, before he actually runs it a second time, which is, we're going to run it a second time with different parameters. Before he runs it a second time, what we're going to do is we're going to talk a moment through what the code looks like. So you can actually see what the macro code is that was generated as a result of what we just did, the exercise we went through. So the base table that we're using, that's the name of the base table, and if we can actually zoom in on that, that'd be awesome. So that's the name of the base table at the very top. The next line is the shift that remember what we did? We took and we actually did the equivalent of a self-join where we looked at the previous trade that had occurred. That was done in this line. We were doing it for a particular date, particular symbol, and particular exchange on the New York Stock Exchange. This was done on the full 52 billion rows. Then we measured volatility by this formula right here, absolute value of price minus price, previous price divided by previous price. Then the next thing that was going on was filter the population down so that we could look at a smaller, a 1 year worth of data. And then we decided volatility should be greater than 10%. And we tabulated the population. We actually linked at the very end. So the language is extremely intuitive. And the structure of it is extremely straightforward to navigate. So what we're going to do is we're going to execute that. Or did you already? Okay, so we're going to execute that again in the last minute of the presentation. This is basically the quick query that we just put together. So what he did is he created 3 prompts, and he created, the values are here. So he's going to execute these, and he just changed it from 2005 to 2012, and he changed the threshold to 8% instead of 10%. So that process is going to continue. It'll probably take end to end around a minute, maybe a little bit longer, depending on how the internet traffic is. So think about what this means in terms of analytics. Think about what this means in terms of analysis of large bodies of data, arbitrarily large bodies of data. So one of the things that we claim and we say to people is we are the equivalent of a trillion-row spreadsheet. Trillion rows, one place, all of your data, never having to move it. The overwhelming majority of the time that you spend on your systems to analyze data is moving it to a target system to do something else with it. We didn't move the data once. And I can estimate, and I'll leave you with this one number, I can estimate 1.5 million individual models, for those of you who are statisticians in the room, 1.5 individual regressions estimated in less than 1 minute on 1 billion rows of data on $100,000 worth of hardware. The game has been changed. Thank you. Question?
Can you tell us anything about what your secret sauce is, how you've been able to achieve this kind of performance? That would just give us at least a hint of kind of what's going on under the hood.
Sure, we'll give you some ideas without giving away too much. Certainly we're a columnar database, massively parallel. We take advantage of basically the way that we represent the data, the way that we take the data in, ingest the data is, we currently have ingested over 11.5 trillion rows of data from all of our clients and partners. And that volume of data, if it's not organized and it's not very, very fast, it's not useful. It just sits there in cold storage. So those are 2 elements of what we do. Definitely massively parallel and definitely columnar representation.